Hello, welcome to my course on the Mosfet. Uh, it covers the operation and dependence of physical parameters of Mosfet FETs. My name is Dr. John Aiken. I worked on the area of FETs for more years than I am comfortable telling you about with IBM when I was working. I'm now retired, and I'd be delighted to share what I know with you and about FETs. If you're looking for some printed material to help you through this as well, I recommend there's quite a few of them out there. One of my favorites is one by Donald Neiman called Semiconductor Physics, and it is published by McGraw-Hill. But there are other ones out there that are also useful. Tower and Ning, Fundamentals of Modern VLSI Devices, printed by Cambridge University Press. Simon Z, Semiconductor Devices, Physics and Technology. Simon Z, VLSI Technology, that's also a very good introductory book. And Streetman, Solid State Electronic Devices by Prentice Hall, and Physics and Technology of Semiconductor Devices by Andrew Grove, published by Wiley. For those who are younger than I, you may not recognize the name Andrew Grove, but Andrew Grove is one of the founding fathers of Intel, and he knows FETs very well, as you might imagine. The content of the course is in broad outline is presented here. We'll cover the structure, function, physical principles, materials, and processing required to understand FET devices and parameters. We'll be covering the origin of charges and surface states from various sources and their impact on yield at T0 or reliability in the field. MOSFETs in your life. Every day you carry around or use devices with several billion MOSFETs. Your mobile phone, by the way, which is presented on the right, this happens to be an Apple, has about 10 billion transistors in it. Your computer at home has about the same number. Your TV has less, but they're serving a different function. In the mobile phone and computer, the transistors are used both to do logical operations and memory. Your TV is mostly a memory operation, and that's why there are fewer of the transistors in it. These transistors are very small. About 5,000 of them can fit across a human hair. This is a picture of the inside of your telephone. As you can see, there are lots of little black packages in there, and those black packages contain our chips, which contain MOSFETs, and they're mounted on green motherboards. If you were to take your computer apart, you would find a very similar kind of arrangement. What's a MOSFET? MOSFET is an abbreviation for a metal oxide semiconductor field effect transistor. Each one of those is describing something about the MOSFET. FET stands for field effect transistor. It refers to a transistor where an electric field applied at the gate opens the conducting channel between the source and drain contacts of the transistor, allowing mobile carriers to flow between them. It's most simply described probably as a switch that switches between two states uh, where the contacts of the transistor are connected or disconnected. MOS refers to the metal oxide semiconductor gate structure, which acts to impress an electric field on the channel between the source and drain contacts. This is a very simple picture of a MOSFET, and I put a generic MOSFET on here because I'm talking about uh, a, uh, a MOSFET which can either be an NMOS or PMOS device, depending on the kind of substrate that it is built on. But the current flow in a MOSFET is turned off and on by the action of the gate voltage here on the uh, silicon area underneath the gate. Voltages are applied to a source and a drain, and those voltages tend to make the current flow when the device is turned on between them. MOSFET-based technologies. MOSFETs are the most commonly used transistors and are used to make modern microelectronic integrated circuits, such as SRAM and DRAM memories, logic chips, microprocessors, RF and communication chips. They are advantageous because of their inherently low power consumption, high speed, and high density. CMOS, which is an abbreviation for complementary metal oxide semiconductor technology, provides the bulk of the integrated circuits made in the world today. CMOS is a technology that contains both NMOS and PMOS devices, and NMOS technology contains solely NMOS devices. But they have largely replaced bipolar technology in the past 20 years. Bipolar devices have some niche applications, including bi-CMOS circuits, but we won't discuss them here. We'll talk about NMOS technologies. Just to give you an idea of what these things look like, this is a picture of a semiconductor wafer, and on that semiconductor wafer you see patterns, shiny patterns of different colors. Those different colors represent different materials, and chips are fabricated in parallel on a 12-inch silicon wafer. There's about 400 chips on each wafer, and the wafer is diced into individual die and packaged to give you something like I showed you in the picture of the inside of your telephone. There are various types of chips on a wafer. Different circuit designs on each wafer are shown here. These are four or five different wafers presented there. Individual transistors are too small to be seen, as you can imagine, since 4,000 of them can fit on a human hair, but they are integral parts of each circuit on the chip. This is a picture of a diced and packaged memory chip that you might find inside your phone or computer. The gold and black areas are areas that either insulate or conduct electricity to contacts on the chip. The blue patterns on the inside are actual transistors or other circuit elements that are needed for the operation of the chip. And as I said earlier, these chips are mounted on a motherboard, that green thing there, that carries voltages and connects the chips. The individual, the chips are all connected through these uh, metal wires to the devices on the inside of the chip and make it work. Okay, Pat, that's the end of this one.
Okay, cool. That's good. We can do another one.
Okay.
So that's great. I will. You want to pull up the next one?
Yep, I'll pull up the next one if I can figure out how to do that.
So now you just hit. I mean, basically, hit the X in the top right. Yep.
Okay, here we are at the second one.
Okay. Yep. So now just do the presentation. Do your play from beginning again, and then you just start.
MOSFET devices. In this section, I'll describe the structure of MOSFET devices, what they look like, what they're made of, and a little bit of what they're actually doing. So the MOSFET is really a circuit element inside all of those little black packages that I showed you inside your telephone or your computer. The MOSFET's a transistor, and it's used as a switch to connect circuit elements to each other and to power sources in integrated solid-state circuits, such as logic circuits, memory circuits, and signal processing circuits. They're used in circuit technologies such as NFET, PFET, CMOS, and BiCMOS technologies to perform various functions. CMOS is the most popular technology in use at this time. They're designed to make fast switching connections. That's why your phone can do as much as it can, because the transistors inside of it are able to switch from one state to another when they are commanded to do so. Here's a simple picture of a switch. Just like turning on a light bulb when in your house, when you throw a switch, the light bulb in your house is connected from a power source at the electric line that comes into your house to the light bulb. When it's closed, the switch, the power is directed to the light bulb in your house. And in this case, when the switch is thrown, the FET or the switch connects one circuit element in the in the package or the phone or the computer to another circuit element, and it makes it either go off or on. So in the metal oxide semiconductor FET, it's basically an off and on switch, just like the one that you flip on when you turn your light bulb on at the house. The voltage applied at the drain node up in here is connected to the source node when the gate is closed. And when the gate is closed, that provides a low resistance connection for the power supply to whatever the other end of the switch is connected to. The source node is connected from the voltage on the drain when the gate is open. or is disconnected from the voltage on the drain when the gate is open. So in your house, this would turn the closing the switch would turn the light bulb on, and opening the switch would turn it off. And in the uh, circuit that is under operation at command, when the switch is told to close or open, it changes the circuit configuration from one state to another. Here's a picture of the generic MOSFET again. This is to just tell you what the uh, uh, parts of the MOSFET are. The switch is really uh, the voltage that turns the switch off and on is applied up here to something called the gate contact. The device responds by taking any voltage source or current that is applied to the source diffusion and directing it through the gate diffusion. The insulator is something that insulates, as you might have guessed, the gate contact from the silicon substrate below it. And that insulating property is a very important part of how this device operates. This kind of shows you again what the MOSFET looks like. There's the gate contact. There's a source contact. These are usually made. The source and drain contacts and the gate contacts are made to silicon, or are made to metal contacts to these silicon diffusions or to the polysilicon gate. I haven't shown the metal contacts here for the sake of simplification. The MOS part of this is depicted here inside, and as you can see, it refers to the stack of materials here, the metal, the insulating oxide, and the semiconductor. The current is carried in the semiconductor. The oxide just provides an electric field to the semiconductor, which changes the conducting state of the semiconductor and turns this switch between the source and the drain on or off. This is a picture of the two important types of MOSFETs, at least for silicon. MOSFETs come in two flavors. They either come in as NMOS devices or PMOS devices. The operation of both are very similar, but they differ in the materials that they're made of and the mobile carriers that they support. NMOS devices, electrons are the mobile carriers. So the electrons are transported through the source, through the silicon when the gate is switched in the on position to the drain. In the PMOS devices, it's built on a different type of silicon, N-type silicon, and holes on the mobile carriers, and they're built on N-type silicon. Through this and most of the course, we'll be dealing mostly with the NMOS devices, and I'm going to give you the opportunity to try and make the conversions for the PMOS device, which behaves very similarly. The only thing that changes in the PMOS device is the type of silicon material that's used and the voltages that are applied to the contacts of the device, both The gate, the source, and the drain in the PMOS are different than the gate, source, and drain voltages in the NMOS. This is just a colorized version of that emphasizes the differences in the materials that are used. The yellow is indicates that there's a PMOS, P-type silicon that's carrying the current in the NMOS device. And in the PMOS device, the blue material indicates where the holes are transported from the source and drain devices under the action of the gate contact. And when the gate contact turns the channel on in this region. Okay, end 2.
Cool.
Did you understand any of that?
You know, I like to think that I'd like to think our brains are similar, but I don't. I think they're similar in capacity, but I think the things we focused on are very different.
Yeah, you don't see what I see. You haven't seen them.
Yeah, not to this extent, but no, it's great. You want to do one more? 10 minutes?
I'll do one more, and that's really all I'm prepared to do because I noticed when I went through this and started preparing for it, the fourth one after this needs some work. So I'm going to have to work on that before we do that again. All right, so I'm going to go back over here. This is a short one, so it won't take very long.
Okay. I'm going to turn my camera off again, and then, or I'll let you get it up. But yeah, no, it's good. I mean, it's well rehearsed. I think you're doing great.
Okay. Let's see. There's the
And then you go start from beginning.
yeah, I'll start from the beginning.
Okay.
Okay, we ready to go on this? Or
Yep. Sorry, I was muted. Yes, you were good to go.
okay, so what do I do? Just start talking?
Yep. So lesson 3, that kind of thing, right?
It's what?
Yeah, just say, lesson 3, right? This is lesson 3, or I
Yeah,
assume
okay.
Yeah.
This is the third lecture on FETs, and it introduces you to CMOS. That's just reminding you what that means. That's complementary MOS circuits and technology. That means, as we talked about earlier, that both NMOS and PMOS devices are used in these circuits to switch things on and off. CMOS circuits and technology. In the early days of MOSFET technology, when I first started working on this eons ago, NMOS FETs were built on P-type silicon wafers, and PMOS were built on N-type silicon wafers. That meant that if you wanted NMOS devices, you had to have a certain wafer type, and PMOS devices, you had to have the different opposite wafer type. As the technology matured and CMOS circuitry became popular, the technology matured to build NMOS FETs and PMOS FETs on the same wafer. The NMOS and PMOS devices had to be electrically isolated from each other to allow the CMOS circuits to function. This was done by creating N and P type doping regions on the same wafer and isolating them electrically from each other by shallow trenches filled with oxide. A schematic of this is shown here. It shows how NMOS and PMOS devices would be juxtaposed next to one another, and the region between them is filled with something we called it STI. It's a shallow trench insulator. It's really an oxide, but it keeps the NMOS device from talking and making electrical contact with the PMOS device. Those electrical connections are part of the circuitry that is in the metal levels, which are not shown here. But they would be used to make whatever connections are required between these devices on the wafer. As we mentioned earlier, a MOSFET acts as a switch. Both NMOSFETs and PMOSFETs serve the same function, although the voltages required are different for each. In CMOS devices, in CMOS circuits, both the NMOS and PMOS devices are used as switches at the same time. This reduces the power used in the switching operation. So this is a kind of go-to scenario for circuit designers to use this. And that's why the CMOS devices are so popular. As I mentioned earlier, I'm now showing you how the MOSFET device as a switch would connect a power supply at one end to some other point in the circuit out here. So on the metal or the metal contact here is connected to something called the gate voltage, which turns the switch off or on. And on the on state, the point X in the circuit is connected to some power supply in the circuit. Here I've donated it as VD, standing as a drain voltage. The PMOS switch, the off state X is not connected to VD. It just kind of is floating, and the circuit would be inactive in that case. But the PMOS switch acts similarly as the NMOS switch that I've shown here. The type of silicon used to fabricate the switch would be different. The signs of the voltages that are applied to the switch would be different, but the net effect electrically is to connect power supply voltages to some given point on the circuit. And this would happen, many of these switches are cascaded together. So if you wanted to turn on a device that was different than the first one encountered from the power supply, many switches would have to be turned on, and that would transport the voltage, power supply voltage, to the circuit point of interest. Flipping the switch. How is that switch flipped? How does the device switch from the high resistance off state, where the circuit point is off, to the low resistance on state? This occurs through the action of the gate voltage, as I said, in the underlying silicon in the MOSFET. We'll discuss how this happens in the following sections.